In the name of Allah Almighty, the Beneficent, the Merciful, welcome to PH 101 Lab. I am Ahmad Ali, and our experiment number 5 is to study the average velocity of a glider using an air track system. So today we will be discussing the theory and calculations and the experiment of finding the average velocity of a glider using an air track system. So the objectives of this experiment is to find the series of average velocities of a glider. So a glider is an object that can slide over a surface. So we will be demonstrating it in the second part. So we have to find the series of average velocities of a glider, and then we will use those velocities to deduce its instantaneous velocity. Means that we will be finding the average velocities of a glider, and using average velocities we will be plotting a graph at the end of this experiment. So the graph will be between the average velocities and the distance between the photo gates, which we will be discussing shortly, and that graph will give us actually the instantaneous velocity. So you should know the purpose of this experiment or the objectives of this experiment. So let's discuss some prerequisites first. So there are two terms. The first one is the average velocity, and the second term is the instantaneous velocity. So you should be clear about these terminologies. So what is an average velocity? So simply we know that velocity is equal to displacement per unit time. Simple. So this is velocity and it's measured in meters per second, or you can use any other system. So what is average velocity? Simply I can give you an example. Let's say I have a point A, a point B, point C and point D. Let we have a car, and the car moves from point A to point B. Let's say in the first instant, here the car was at rest at point A. So our car was here at point A. Now it moves here. Now it starts from A and reaches point B. So it covers some displacement. Let's say I am calling this displacement S1, right? This is S1, and the time taken by this car to move from A to B is, let's say, delta T1, or let's say I am representing it by T1. Now after reaching point B, the car again moves from point B, the car moves from point B to point C. Now it's covering a displacement of, let's say, S2, and the time taken is T2. Again after reaching C, the car again, let's say the car is now at rest, and again it starts from C to D in covering a displacement of S3, let's say. So displacement is a vector quantity, you should be caring about the vectors, and let's say it takes time T3 to move from C to D. Now what will be the velocity of this car? So in this case the velocity will be the average velocity. So what is average velocity? It is simply the total displacement covered in total time. So if the car is moving from A to B, B to C, C to D, and I am asking you that what will be the average velocity, so you will be adding the total displacement or the distance, the total displacement divided by the total time. So the distance that car travels from A to D is the sum of these displacements, and the time taken is the sum of these times. So the average velocity will be S1 plus S2 plus S3 divided by T1 plus T2 plus T3. Let's represent this displacement by S. Let's say this complete distance displacement from A to D is S, divided by, and the summation of these three time intervals T1, T2, T3, let's say this is represented by T. So this will be our average velocity. The total displacement covered by the car from moving from point A to point D is actually its average velocity. So we are clear. Let's say the car cover a distance of, let's say it's moved from A to B, and it covers a displacement of 50 kilometers in 1 hour, let's say. So its average velocity will be 50 kilometers, and the time taken, in the time it takes, let's say this is T and this is our S. So the time it takes is 1 hour. So its average velocity will be 50 kilometers per hour. So this will be its average velocity. Now if the car moves from B to C, and let's say it covers 2 hours, and the distance or the displacement it covers is 40 kilometers per hour, or let's say 40 kilometers per hour. So now the average velocity will be 50 plus 40 divided by 1 hour plus 2 hour. So it will give 90 kilometers, and from here we will get 3 hours. So we will get 30 kilometers per hour. So this will be the average velocity if the car moves from point A to B and then from B to C. So we will sum up the displacements and divide it by the total time. So this is the average velocity. Very simple. We are clear about these terminologies. So why we find the velocity of an object? Because finding the velocity is very useful to find the velocity of an object. It tells you how fast something is moving. So we actually need average velocities in our real life. How fast is something moving? So we will need the velocity of that object. So that's why the average velocity is very useful. Now what is the second one? Is the instantaneous velocity. So the instantaneous velocity is it's derived from instant, which means movement. In Urdu we call it lamha. So actually it's the instant, the velocity at a particular instant is actually the instantaneous velocity. So let's say, so what will be the instantaneous velocity? So let's say the car moves from A to B. Now the time it takes is, let's say the displacement is S1 and the time it takes is T1. So we know that the average velocity is S1 by T1. Now what will happen if the distance between these 2 points is very small, such that the distance is so small that if the distance between these 2 points decreases, let's say the 2 points are very close to each other, such that the time del t approaches to 0. It means that the time is not 0, but the time is very close to 0. So at that instant, when the time interval is very short, the displacement will also be very short. So definitely if the time interval is very short, so the displacement covered by an object will also be very, very short displacement or very, very small displacement in such a short time. So it means that if the time interval is very small, such that it approaches to 0, it tends to 0, but it's not 0, then the displacement it will cover is also very small. So the velocity at that instant will be the instantaneous velocity simply. So what is an example of the instantaneous velocity? So mathematically it's very important to know that, let's say, simply if I have the average velocity, so the velocity is defined as S, let's say I am calling this delta S. Let's say delta S is the displacement if a body is moving from A to B and it takes time delta t. Now it's the average velocity. So if I impose a condition that, let's say, if I apply a limit that let's say the del t tends to 0. If this is the limit, this is the condition that this del t is very small, so the displacement taught by the object will also be very small, then this represents the average, this represents the instantaneous velocity simply. This will be the instantaneous velocity at a very short interval. So the simplest example I can give you is, the simplest example is speedometer. Let's say you are moving in a car on a motorway and I call you and I ask you, what is your speed? So what will you do? You will just by looking onto the speedometer or by looking into the speedometer, you can tell me that, let's say I am moving with 50 kilometers per hour, or let's say 120 kilometers per hour, let's say. So after some instant, if I call you, if I ask again that what is your speed, then you will say that, let's say my speed is now 140 kilometers. Maybe you are accelerating, maybe it's constant. So it means that whenever I ask you what is your speed, you just look to the speedometer and tell me the velocity of the car. So what you are doing, you are measuring the velocity at a particular instant. If I am asking you what is the speed, you just look onto the speedometer and tell me it's 120 kilometers per hour. Then at the next instant, you tell me it's 140 kilometers per hour. So it means it's the instantaneous velocity. You are telling me at a particular instant. So this is an example of the instantaneous velocity. The velocity of the car using the speedometer. So the speedometer tells the instantaneous velocity. Now there is a very simple question, and I'll leave it to you. You will have to respond this question. Can an average velocity of a body can be equal to its instantaneous velocity? So you should answer this question. You can leave it in the comments. Now this is the instantaneous velocity. Now we are clear about the velocity and the instantaneous velocity, or the average velocity simply. Now after discussing this, the prerequisites, let's move towards our experiment. So our experiment was to find the average velocities of a glider, and the apparatus which is required is the air track having holes. As you can see, we will need a glider, photo gate timer, air blower supply. As you can see in this figure, this is an air track system. So actually an air track is a triangular hollow surface. It's triangular hollow, inside it's hollow, and on the surface it has holes. So what happens, we have a blower, which it is connected with a blower from this end. So this is air blower. It provides air to this hollow air track. The air goes inside, and what happens, through holes the air comes out. So you can feel it if you keep your hand close to the air track. Now there are many methods to reduce friction. So one way is to reduce the friction, the contact between two objects, by air. How? When there we have a glider, here we have a glider. So the glider can slide over this air track, which we will be shortly demonstrating in our second part. You will get a better idea. So the glider can slide over this surface. So what happens when the air goes inside this hollow tube or the hollow triangular air track? This air provides a force to this glider, and as a result the friction between this surface and the glider surface decreases, and as a result this air blower provides the force to this glider, and it moves or slides over this surface. Now this air track is, from this side it is inclined 1 or 2 centimeter more as compared to this side. So it's like inclined 1 or 2 centimeter above from this side. Now there are two things. One is the photo gate. So what is a photo gate? We will be discussing it. We have two photo gates. The distance between these two photo gates is d. So these two photo gates are equidistant from this center point. So the air track is, in our case, our air track system is 200 centimeter long. So there will be a meter strip which will tell you that its length is 200 centimeter. So if it's 200 centimeter, its midpoint x1 will be 100 centimeter, very easy. 100 this side and 100 this side. So 100 will be its midpoint. Now you should keep in mind that these two photo gates, this photo gate is at a distance d by 2, and similarly this photo gate is at a distance d by 2 from this center point x1, which is 100 centimeter mark. So these two photo gates are equidistant from this central point. Keep in mind, they should always be equidistant from this central point. Let's say this is 5 meters away from this point, 5 centimeter away from this point. This photo gate P1, let's say, or P2, this photo gate will also be at a distance 5 centimeter away from the central point. So keep in mind, the distance between these two photo gates is d. So let's say this photo gate is at mark 140 centimeter, and this first photo gate is at mark 60 centimeter. So the distance between these photo gates is final minus initial will give us 140 minus 60 centimeter will give us 80 centimeter. So the distance between these two photo gates, so this will be our d, 80 centimeter simply. And d by 2, so you will divide this by 2, it will give 40 centimeter. So this photo gate is at a distance 40 centimeter from this central point, which is 100, and also this photo gate is at a distance 40 centimeter from this central point. So this should be very clear. Now how it works, the air blower provides air, the glider experiences that force, and as a result it starts moving due to the air, and the air is used to reduce the friction between the glider and the air track. Now as it moves, these two photo gates are connected with the timer, and we call it the photo gate timer, and it's placed on a horizontal surface. Now this is very simple. Now what is a photo gate and what is its purpose? Photo gate. So what is a photo gate? In simple words, it is used to study the motion of an object, and it is a device that measures the time as an object moves through it, and as an object moves through it. And how it works? Simply it is used that if, let's say this is a photo gate. So here we have a LED, light emitting diode, and here we have the sensor. So what happens? LED beam comes out from this LED, and so what happens? An infrared beam is emitted by this light emitting diode. So we cannot see infrared, but you can observe it because it's connected with the photo gate timer. Photo gate timer will tell you. So now let's understand its construction. We have an LED and it's infrared, it's producing infrared light. Now as this light beams goes straight, here we have a sensor. The sensor detects that light and it's connected with the photo gate timer. These two photo gates are connected to these green wires with the photo gate timer. So let's say this is connected with this photo gate timer. This is our photo gate timer. Here we have a display screen which tell us the time, and here we have some switches. We can move the switch to the here we have some modes: gate mode, pulse mode, or the pendulum mode, PEN. So what happens is an object moves through this beam, so the beam gets blocked. So at the instant it gets blocked, the timer starts, and at the instant it gets unblocked, the timer stops. So as the object blocks the beam, as it moves through the photo gate, as it blocks the beam, the timer will start, and the photo gate timer will tell us the timer will start. As it moves through this photo gate, the beam gets unblocked, and what happens? The time stops. So actually, if we are using it in the gate mode, this is the gate mode, there will be a switch, so you can move it to the gate mode or the pulse mode. So the gate mode is actually, as it moves, it blocks the beam, the timer starts, and as it unblocks the beam, the timer stops. So we will be experimentally demonstrating it as well in our second part, but for the time being, let's understand this. So block unblock is the gate mode. The timer starts as it blocks the beam, and as it unblocks the beam, the timer stops. So it will actually give you the instantaneous time. And now in the pulse mode, there is another mode in the pulse mode, and in our experiment, we will be using this photo gate timer in the pulse mode. So for the pulse mode, 2 photo gates are required. So we will need 2 photo gates of exactly the same length and size. So let's say we have another photo gate here. Now if you are using 2 photo gates, P1 and P2, so we know that the distance between these 2 photo gates is D. Now these 2 photo gates are connected with the timer as we discussed. Now we are using this timer in the pulse mode. There will be a switch and you can move it to the pulse mode. So our experiment will be, we will be using for our trials the photo gate timer in the pulse mode. Now in the pulse mode, let's understand it. As it blocks the beam, the first photo gate, as it blocks the beam of the first photo gate, the timer starts. And as it moves, the timer will not stop, unlike in the case of gate mode. Again, as it blocks the beam, the timer will start. As it unblocks, the timer will not goes off. The timer will not goes off. So what will happen? As it blocks the beam, the timer will start. And as it reaches the second photo gate and it blocks the beam of the second photo gate and unblocks it, the timer will stop. So at the first photo gate, the timer starts, and at the second photo gate, the timer stops. So actually, it is giving us the time interval between these 2 photo gates that the object covers. Let's say it's a car or a glider, let's say, that is moving between these 2 photo gates. So if you know the distance between these 2 photo gates, D, and the time interval between these 2 photo gates will be we can note it from the photo gate timer. Simply it will give you, it will be a very short time, let's say 0.91 or 0.315 seconds, let's say. So if you divide that time, that distance by that time, you will get the velocity of this, the average velocity of this glider. Instead of using two photo gates and you switch it to the gate mode, then these two photo gates will be working as a single photo gate, keep in mind. So in the pulse mode, we need two photo gates at least. And in the gate mode, a single photo gate can work as well. So this is actually what we will be doing. Now that let's understand the procedure. So this is the pulse mode and the gate mode, and the photo gate is called the photo gate because there is a LED, infrared, that is producing an infrared light, and that is detected by the sensor, and as it blocks the beam, the sensor tells the photo gate timer to record that time. Simple. Now the apparatus, we are now clear. So this is actually the apparatus. Distance between two photo gates is d by 2. The middle point we are calling that point is x1, is our 100 centimeter. Keep in mind, if you are starting your glider from this position, you will have to always start this glider from this position throughout the experiment. So fix it. Let's say this is your x0 mark. So just to remember, simple. Let's say it's 14.5 centimeter mark. So you will always start this glider from 14.5 centimeter mark. So what we will do, let's say the first photo gate is at 140 centimeter initially for the first experiment, and the second photo gate is at 60. So 140 minus 60 centimeter will give us 80 centimeter. So this is actually the d, the distance between these two photo gates. So you will note that distance 80 centimeter here. Simple. Now how to measure the time t1? So we will be, again, as we are performing experiment, we will have some trials, t1, t2, t3, t4 and t5. So for this distance, fixed distance, now 80 centimeter, we will repeat this experiment 5 times. It means we will note 5 times this experiment. So what will happen when the distance between these two photo gates 80 centimeter, we will turn on the blower. Now keep in mind, there is a speed. You can turn the knob at either turn the knob to 3, 2 or 1. So you have to check it. If at 3 you will keep on increasing, and let's say at mark 3, glider starts moving. So this will be your fixed speed. Keep in mind, you will always be performing this experiment for that speed. So you can keep it at 2, 3, 4, but you will have to keep it fixed throughout the experiment. Now as the glider moves, the air provides the force, the glider will move. As it passes through the first photo gate, keep in mind, for our experiment, we will be using the photo gate timer in the pulse mode initially. Pulse mode, keep in mind. Pulse mode can be switched through using the photo gate timer. Now as it moves through the first photo gate, the timer will start, as we know now, the pulse mode, and as it moves through the second photo gate, the timer will stop. So this will be our T1. You will note down the value. Now there will be a reset button on the photo gate timer. There will be a reset button. You will press the reset button. Then you will have to repeat this experiment. Again turn off the blower, or here will be a switch. Just switch it off and again switch it on. Reset the timer. Move the glider back to its initial position. Switch on the blower. The glider will start moving. Again note down the time between these two photo gates. The photo gate timer will tell you the time. This will be your T2. Again repeat this experiment. You will get T3, T4, T5. Now what will you do? You will have to take the average of these values. T1, T2, T3, T4, T5 divided by 5. So we will get the T average. Now if you know the value of the T average, we know the distance is fixed 80 centimeter. So our average velocity will be this distance divided by the average time. So we will get the average velocity for the case of when the distance between these two photo gates was 80 centimeter. Now what we will do, the requirement for this experiment is we will move the photo gates towards each other by an increment of 5 each, from each side 5 centimeter. So we will move this photo gate 5 centimeter here. So it will come to, if this is 140, it will come towards 135 centimeter mark. And if I move this photo gate here, it will be at 65 centimeter mark. Now it will now subtracting. Now these two photo gates are now here. So actually the distance between these two photo gates, this photo gate is reduced by 5 centimeter, this photo gate is reduced by 5 centimeter. So now the distance is 10 centimeter in total, because 5 centimeter each side, so the total is 10 centimeter. So we will be reducing the distance by 5 centimeter each, or we can say by 10 increment. Now it will give us 70 centimeter. Now our distance is now fixed at 70 centimeter. Now you will have to repeat this experiment for just like we did it for 80 centimeter. T1, T2, T3, you will note down the value. Then you will again by increment of 5, this will become 60. Then it will become, here we will have 60 centimeter. Then we will have 50 centimeter. Then we will have 40 centimeter, 30 centimeter, 20 centimeter, 10 centimeter. Now here is something you should know, that the photo gates are coming closer and closer and closer. So a stage will come when the two photo gates will be very close to each other, very close to each other. Keep in mind, the two photo gates will be very close to each other, and these two photo gates are connected with a photo gate timer. Now when this glider moves, we know that the glider blocks the beam and the timer starts. We know the process. Here we have an infrared beam and it's get blocked, and as it unblocks, the timer starts and stops. So it tells you the time interval or the instant time. Now what will happen? Now the distance, let's say for 10 centimeter. When the distance is very short, let's say 10 centimeter. So for 10 centimeter, the two photo gates are very close to each other. So when the glider moves between these two photo gates, there is also a possibility that the photo gate, the glider blocks the beam of this photo gate P1 and this photo gate simultaneously, and means at the same time this glider is blocking the beam of these two photo gates. Or if it's not the case, also the distance between these two photo gates are very small. So we are reducing the distance to actually find the instantaneous velocity. So if they are, let's say we cannot reduced it further after 10 centimeter. So if the distance between them is 10 centimeter and we are using the increment 10, so then what will happen? I cannot reduce it further because the distance between them will be 0. So 10 centimeter will be the minimum distance between those photo gates, between these two photo gates. So if the distance is very short, so actually from here I can calculate the instantaneous velocity, which will be close to the actual instantaneous velocity, which we will be calculating or deriving from our graph. Now what will you do when the distance between them is 10 centimeter, they are very close to each other, you will switch the photo gate to the gate mode. Now we know that in the gate mode, as the beam gets blocked, the timer starts, and as it unblocks, the timer stops. So you can say that these two photo gates are now working as a single photo gate, or this first one is working, simple. So if the glider is moving between these two photo gates, the distance is 10 centimeter. The distance between these two photo gates is 10 centimeter. Or if you are using a single photo gate, let's say if you are using a single photo gate in the gate mode, so now, and the length of the glider, you know the length of the glider, let's say its length is 2 or 3 centimeter. And as it moves through this photo gate, now let's say if you are using a single photo gate timer, which we will not be using here, but if you are using a single photo gate timer, it blocks the beam, unblocks the beam, we will get a time. So this time will be actually the instantaneous time. And if I divide the length of this glider 3 centimeter divide by that time, I will get the instantaneous velocity of that glider, just like the speedometer of a car. But here the problem is, because we are using two photo gates and we need some distance, so for that case what we will do, when the distance between them is 10 centimeter, we will switch it to the gate mode, and as it blocks the beam and unblocks, so in that case what we will do, we will divide that distance. Now the distance is 10 centimeter and we will divide that time. Now the distance is 10 centimeter, we will divide it by that time, which we will get it from here. So this time will be very short. This time will be very short. Or we can say that the velocity will be maximum here, simply. So if the distance is large, So it will take more time. So we can say that the velocity will be, for this case, because the force is fixed. If the force is fixed, the frictional force is fixed, and the distance is fixed. And if the distance, for the first case, the distance 80 centimeter, it's more. So it will take more time for the glider to move from this photo gate to this photo gate. Now if the distance is 70 centimeter, now it's fixed, it will take less time for the glider to move from this photo gate to this photo gate. So the velocity will keep on increasing by decreasing the distance. So you have to repeat this experiment for this case, but for the last case, when the distance is very short and you cannot reduce it further, you will switch the photo gate timer to the gate mode. Simply this is the requirement of this experiment. And then you will calculate the value. Now at the end you will have to plot a graph. At the end you will plot a graph. You will get a series of average velocity for this 80 centimeter. You will get a series of average velocity. Note it down. You can call it V average 1, V average 2, V average 3. Now you have the distances 80, 40, 60, 70 or the displacement. So you will plot a graph. Let's say this is our x-axis. On x-axis, let's say this is 10, 20, 30, 40, 50, 60, 70, 80 centimeter. Or this is our D simply in centimeters. Using a proper scale, you know how to use a proper scale. This is average velocity. I am simply calling it V average in meters per second simply. Now you will get dots, you will get points on this graph. For 80 centimeter, let's say the velocity is this. So the graph will not be perfect, but if your calculations, data and calculations is very neat and clean, and you have performed this experiment, not neglected the precautions, you will get the accurate values. So what you will do here, we will have the average velocity. So using proper scale, let's say this is 50 centimeter, this is our 55 centimeter, 60 centimeter, 65 centimeter, or it can vary according to your experiment. It can be less, the velocities can be more or less. So we will get points like this, let's say. So there will be some outliers as well. So the graph will be like this. By joining those points, by joining those points, you will get a graph like this. Now let's say these are our points. Let's say these are points, and some points will be on this graph. Some will be outliers, some will be not on this point. Some points will be on this line and some will not be on this line. Let's say these are our points on line, right? So we will get a graph like this. Now how can we find the instantaneous velocity? Now we will extrapolate this curve using our scale. This point, this is actually the y-intercept. This is y-axis. So this is actually the y-intercept. And this y-intercept, the value here, the value at this point, let's say its instantaneous velocity from, let's say if this is 65, this is let's say 65.5 centimeter per second or meter per second. You can use the scale centimeter or meter according to your ease. So this y-intercept, extrapolating this curve, it will intercept this y-axis, and this will give us the instantaneous velocity. So actually this point, at this point we will get the instantaneous velocity because the distance is now very short. If the distance is very small, this will be the instantaneous velocity. Now keep in mind, if this is 10 centimeter, if this is 10 centimeter, so actually we are having two photo gates. So the distance was 10 centimeter. But for the instantaneous velocity, if you switch it to the gate mode, it works as a single photo gate. Now from this curve, you can see that if I move, this is our origin. So if this D is also 0, this D can only be 0 when we are using a single photo gate. So if there is a single photo gate, there is no D. So we are now at this origin. And the velocity at this instant will be, when the D is 0, is y-intercept. And this y-intercept will give us the instantaneous velocity. Keep in mind. So if you are plotting graph, you should know Why the y-intercept is instantaneous velocity. If you are plotting this graph like this, it makes no sense, because it means that the y-intercept is 0. And the displacement is, the average velocity, the instantaneous velocity is 0. As the distance reduces, less time is taken by the glider and the average velocity increases. So you will get a graph like this. This is our experiment number 5 to study the average velocity of a glider using an air track system. So this was actually the setup, the photo gate timer, the air track with holes, photo gates using air to reduce the friction, the contact forces, the air blower, and then we will have to fill this table according to the calculations. And the purpose, keep in mind, the purpose is very important. So the purpose is to study the average velocities of this glider. Why we need to study the average velocities? Because if I calculate the average velocities and then plot those average velocities with a distance between these two photo gates, then what I will get? I will get a graph. And by extrapolating that graph, the y-intercept will give us the instantaneous velocity. Thank you.